So I have written here the time-dependent Schrödinger equation. And one of the reasons why this equation is so important is it tells us how how any wave function evolves in time, right? That based on how the wave function is in terms of space, right? How its derivatives, and I forgot the capital here, how its derivatives are in position and the potential energy function, that determines how the wave function evolves in time. And you can write this out a little bit more explicitly by writing d by dt as psi, right? This is the rate of change of the wave function in time, right? And we can write that out as I h bar over 2m, where I also took note of when I divide by I, I'm just multiplying by negative I, right? IH bar over 2m, d squared by dx squared, capital psi, minus IV over h bar, capital psi, right? Hopefully you can get that. It's not too hard algebra, just remembering dividing by I is multiplying by negative I, right? And this, right, gives us very explicitly how the wave function evolves in time. And we will be using that in this video. Now, there's a very important thing that we know all wave functions have to follow, right? And note this has to be true for this capital psi, right, and for the lowercase si's. But the trick that I showed last video, I want to just clarify, the trick I showed last video about when we're normalizing and that you can just normalize the lowercase psi instead of the capital psi, that only works for the energy eigenfunctions, right? In general, we have to normalize this capital psi, right? Only capital psi e is the one that we just have to normalize our position function, right? And so now we know that our condition is that the integral from negative infinity to infinity of psi norm squared dx is 1, right? This has to be true for every point in time, right? And if we normalize psi, it has to stay normalized, right? That's the only way for a theory to make sense, right? We can't have a theory where we're having particles just, having some probability of not being between negative infinity to infinity. We're not talking about decay, right? So this is a very important thing to hold for all values of time, right? Another way to write that is once we normalize psi, it has to stay normalized. The integral from negative infinity to infinity of psi norm squared cannot change in time. And so how do we write, right, in calculus, how might we write how that something can't change in time? Well, we set its derivative equal to 0, right? That's what it means for something to not change in time. Now notice this will just be, in here, this will just be a function of time, right? Because we're summing over the x part. That's something we have talked about a lot in this course, in section 3 particularly, that when we're summing over x, right, this is a function of x and t. So we only need an ordinary derivative. Ooh, didn't mean to erase that. This is 0. Right? The derivative has to be equal to 0. And now, for the Schrödinger equation to work, for it to be an acceptable equation in quantum mechanics, it has to hold this property, that normalization can't just change over time. That won't happen, right? And so in this video I want to verify that the Schrödinger equation indeed does tell us that normalization won't change over time. Otherwise, it wouldn't really make sense as an equation. Right? And so let's go ahead and start doing that. Now, this will use a bit of calculus, so I want to make sure you're familiar with partial derivatives, and also the product rule for derivatives. I'll have linked my video about my video on derivatives where I do cover that. Okay. And now we also need one other fact. I don't know if I covered this in any video before, but from multivariable calculus, it turns out that if you have a derivative outside of an integral, you can actually bring it inside the integral as long as you change it from an ordinary derivative to a partial derivative. That's just a concept in calculus 3. So the integral from negative infinity to so this is the integral from negative infinity to infinity partial t. Now again, psi norm squared, this is just a product. This is psi inner product with so it's not inner product, and it is inner product, but this is just psi complex conjugate times psi. Right? The inner product is with the integral. This integral is psi inner product with psi. Right? And then dx, right? Okay, so now, and also hopefully you should know integration by parts. That's also, I'll have that video linked in the description here. Right? Well, now we are taking the derivative of a product, and there ends up being, it turns out that there is a rule of how to take the derivative of a product. It's called a product rule. Sorry about this, I know it's a little messy. And so let's, we'll start with the product rule, the integral from negative infinity to infinity of, and when we're taking this, we have the first times the derivative of the second, so psi star, times the derivative of the second, d by dt of psi, plus the second, so psi, times the derivative of the first, d by dt, psi star. Dx, right? This is just the product rule for differentiation. And now we're going to use the Schrödinger equation to turn these into actually position derivatives. And to do that, I actually need to do one more thing with the Schrödinger equation, which is take the complex conjugate. What happens when we take the complex conjugate of the Schrödinger equation? So I'll write both of these in their complex conjugate form. So negative h bar squared over 2m, right, that's real, that's good. D squared by dx squared, that's good. Psi has to turn into psi star. So if you remember, we will be able to do this with when we have multiple things to take the complex conjugate of, just because the complex conjugate of a product is the product of the complex conjugates. Plus v. Now we're assuming v is real, right? That's going to be important. V is real. So v times psi star, right? And that makes sense. Potential energy has got to be real, right? It wouldn't make sense for potential energy to not be real. Is equal to I h bar. Well, I becomes negative I h bar, d by dt, I think I have enough room for this, psi star. Right? And now we can either rearrange this equation to get to basically find what d by dt of psi star is, or you can just take the complex conjugate of this equation. It turns out it will be the same either way. So you can check that out if you would like to. So this will be negative I h bar over 2m d squared by dx squared psi. Hopefully you can read that. It's not too bad, I don't think. Plus, right, plus instead of minus, I v over h bar psi star. Right. Okay, so now, as you see here, we have a d by dt of psi, and we have a d by dt of psi star. So we, in fact, can substitute this back in, or substitute it into the to our integral, and this is going to be the part that uses the Schrödinger equation, right? So now our result is dependent on the Schrödinger equation, right? And our goal is to show that this is equal to 0, because if it does, then we know that the Schrodinger equation preserves normalization, right? So this is psi star. So I promise this is probably some of the most math we'll have in this section, but I wanted to do this video because this is such an important property of the Schrodinger equation. Okay, so d by dt of psi is I h bar over 2m d squared by dx squared psi minus iv over h bar psi. Right? Okay. Next is our next term where we have plus psi times, and now d by dt of psi star, which here we know is minus I h bar over 2m d squared by dx squared psi. I don't want to close parentheses there. Plus iv over h bar psi star. And then dx. Okay, so our next line, right? I'm going to multiply this out. I'll combine some terms, and so I'm going to skip a few steps of the algebra just to make this not too painfully long. But all I'm going to be doing is multiplying this out, and then I'll just rearrange the terms a little bit next to each other. And so the first thing is with this term, the psi star times IH bar over 2m, and this psi times minus IH bar over 2m d squared, right? Each of these terms have a common factor of IH bar over 2m, so I'm actually going to factor that out. So I've got IH bar over 2m. What do we have here? IH bar over 2m. And I'm going to have this because I'll have a few terms here. IH bar over 2m, psi star d squared by dx squared psi. And then here there'll be a minus sign, minus psi d squared by dx squared psi star. Right? That's this term and that term. And then the next ones will have minus iv over h bar psi star times psi, right? Because this is all going to commute. These are all just functions, right? And so this will be minus iv over h bar psi star times psi is psi norm squared, right? And then here we'll have plus iv over h bar psi times psi star, right? Which is psi norm squared. Rid of this, dx. Well, hey, this term and that term will cancel out, right? And so now I'm going to erase our Schrodinger equation work on the side here. We are almost getting to it, right? So this is equal to, and then after that I'll erase this work down here. I just want to copy it down here. We've got the integral from negative infinity to infinity of, and we can take out this IH bar. We can take out this IH bar over 2m. IH bar over 2m. And then we have two integrals here, right? We have two terms. So in fact, why don't we just break it up into two different integrals? Because we can do that. That is the product rule of, or the sum rule of integrals. Right? So this is psi star d squared by dx squared psi minus and then dx minus the integral of from negative infinity to infinity of psi d squared by dx squared psi star dx. Right? And then all of this is going to be multiplied by the IH bar over 2m. Okay. So hopefully you have all that written down. Next, we have to remember our integration by parts formula. And if you don't remember it, I will give it to you right here. And now this will work with, when I did not do that. There we go. Okay. So the integration by parts formula is that if I have the integral, this will work with partial derivatives as well, just as it works with ordinary derivatives, of the integral from negative infinity to infinity. Actually, it's, yeah, I'll write it in terms of negative infinity to infinity. It's more general than that, but times f partial g partial x, right? If I have two functions, this is equal to f times g, all of that evaluated from negative infinity to infinity, right? So that would be f of infinity, g of infinity, minus f of negative infinity, g of negative infinity, right? And then minus the integral from negative infinity to infinity of g times df by dx, right? And so now, what we're going to do here for our first integral, our f will be psi star, and our g will in fact be d psi by dx, right? Because the second derivative is the derivative of the first derivative, right? So this right here is dg by dx, right? And so using this, we know that our integral now, we have IH bar for 2m, integral from negative infinity to infinity. Actually, I'll start it with this. This is just using our integration by parts formula. This is f times g, right? Which will be psi star times d psi by dx, evaluated from negative infinity to infinity, right? Minus the integral from negative infinity to infinity, and then we have g times df dx, so this is d psi dx, d psi star dx, right? And then minus, right, because there's a minus sign right here, minus, and now our f over here, our f will be psi, and our g will be, not parentheses, that's an equal sign, g will be d psi star by dx, right? Because then this will be dg by dx, right? And so now if we just repeat this process, right? But instead of it being this positive over here and the negative over here, right? Because there's a minus sign, so it'll be minus the positive, then minus the negative integral, right? So this is f times g, which is psi times d psi star dx from negative infinity to infinity, plus, because remember we're subtracting the negative, plus the integral from negative infinity to infinity, and hopefully you should see something quite interesting here. G d psi star by dx, oh, and I did forget my dx in this integral, d psi star by dx, d psi by dx, dx. Okay, so now all of this work has showed us, right? Notice this integral, right? It's just in the opposite order, but it doesn't matter. These are just functions, so they commute, right? This is the same as that. One's positive, one's negative, so they cancel, right? And we're evaluating these functions at negative infinity and infinity. But psi star, I'll start with psi. Psi of infinity, well, because psi is normalized, right? We have to, right, that's our whole assumption is that these functions start normalized, right? Psi at infinity is 0. Psi at negative infinity is 0, right? Psi has to, doesn't have to be a Gaussian. It can be doing whatever it wants here, whatever it wants. But when it gets to infinity and negative infinity, right, it has to go to 0, right? Otherwise, it can't be normalized if it keeps on, not being 0 at positive and negative infinity. It can't be normalized. We've talked about that before, I believe, right? So psi of infinity is 0. Psi of negative infinity is 0. So we're doing 0 times this, which it turns out this will actually be 0, but we don't need to talk about why that is quite yet. So it will be 0 times something minus 0 times something, right? So this is going to be 0. And over here, same thing, psi star, the complex conjugate of 0, right? Because psi at infinity is 0, so psi star at infinity is just the complex conjugate of 0, which is 0, right? So this will be, this psi star has to also go to 0 at positive and negative infinity. That would make sense if it's just, right, the complex conjugate of 0 is 0, right? So at positive and negative infinity, so this will be 0 times something minus 0 times something. This will be 0. And we are left with 0. And so the Schrodinger equation tells us that if I have a function that's normalized and it goes through Schrodinger time evolution, it goes through time, evolves in time through the Schrodinger equation, which we know all wave functions do, it will still be normalized after, which is very important. If we didn't have that, the Schrodinger equation could not be used. We have to have this property, and it turns out this works, which is very good. So I will see you in the next video.